We are going to do mathematical induction. This is a topic that will be almost always in your exam. So you need to pay attention to this topic and make sure that you master this topic, because there is no way you are going to write a discrete paper without this topic. It will be always there in your exam. So please make sure you go to your exam well prepared. So let's begin. So by the end of this unit, or by the end of this chapter, you should be able to explain the general principle of mathematical induction. Also, you have to be able to use mathematical induction to prove a variety of inequalities that holds for all positive integers greater than a particular positive integer. Wait, I'm trying to add other people here. So you must be also able to apply mathematical induction to prove divisibility results about integers. Also, you must be able to to prove using mathematical induction on the issue of inequalities. Also, you must be in a position to explain how to use mathematical induction to prove many other various examples, because there are a lot of examples on proof by mathematical induction. So, what is the principle of mathematical induction? Thank you, Michelle. May you? Okay, it's okay. Thanks. So, principle of mathematical induction. So, given P of n as a propositional function, a proof by mathematical induction has two parts. A basis step where we show that P of 1 is true, and an inductive step where you show that for all positive integers of k, if P of k is true, then P of k plus 1 must be also what? True. So on principle of mathematical induction, what we have here, we have got the basis step, and then you have to give a hypothesis or assumption, and then later you have to do the inductive step where you have to prove using the assumption. Also, principle of mathematical induction is a formal method of proving the left-hand side and the right-hand side. So since it is the formal method of proving the right-hand side and the left-hand side, you need to follow its steps. There is no way you can prove using mathematical induction without following its steps. So you need to follow its steps very well. Let me add someone here, I'm sure. It's fine. So to prove that P of n is true for all positive integers n, where P of n is true, is a propositional function, we complete two steps, which is the basis step. We verify that P of 1 is true. And then there is the inductive step. We show that the conditional statement P of k implies P of k plus 1 is true for all positive integers of k. What we are saying is that for you to complete the inductive step, you need to use the assumption step, where you will be assuming that if it holds for P of 1, it must also holds for P of k. So this one is an assumption. And then you need to prove that if P of k is true, also P of k plus 1 is what? Is true. So to complete the inductive step of a proof using the principle of mathematical induction, we assume that P of k is true for an arbitrary positive integer k and show that under this assumption, P of k must also be true. So the assumption that P of k is true is called the inductive hypothesis, or an assumption that you'll be given. So we have got this example. We have to show that if n is a positive integer, if n here is a positive integer, then 1 plus 2 plus 3 up to n must be always equal to what? N by n plus 1 over 2. So our solution here, we start at the basis step. So let P of n be the proposition that the sum of the first n positive integers from 1, 2, 3 up to n is equal to n plus 1 over 2. Is n plus 1 over 2. We must do two things to prove that P of n is true for n is equals to 1, for n is equals to 2, for n is equals to 3, since we are talking of what? Of positive integers, where n is a positive integer. And you see here we are starting at 1 here, so which means we need to start at n is equals to 1. Because when you put n is equals to 1, that's when we get a what? A 1 here. So after that, namely, we must show that P of 1 is true and that the conditional statement P of k implies P of k plus 1 is true for k is equals to 1, 2, 3 up to infinity. So on our basis step here, P of 1 is true because if we put a 1 at any here, if we put a 1, let's come back here, we've got, if we put a 1 here, and also here we put a 1 for n, what do we get? That's P of 1. So we get 1 is equal to 1 plus 1 plus 1 over 2, which you always give us what? A 1, because here it's 2 over 2, which is equals to 1. Since 1 here is equal to 1 here, then we can say that P of n is true for n is equal to what? For n is equal to 1. So the left-hand side of this equation is 1 because 1 is the sum of the first positive integer. So the right-hand side is found by substituting 1 for what? For n in this expression. So on the inductive step, what we need to give first is the hypothesis or an assumption, and then an assumption for P of k, or when n is equal to k. So for the inductive hypothesis, we assume that P of k holds for an arbitrary positive integer k, or P of k is true for a positive integer k. That is, we assume that the summation of 1 plus 2 plus 3 up to k is equal to what? Is equals to k plus k multiplied by k plus 1 over 2 here. Under this assumption, it must be shown that P of k plus 1 is true. Namely, that, so what we are saying here is that if P of k is true, also P of k plus 1 is equal to what? It must be true. Because we are just saying from here, we have got this number, and we've got this number, we've got this number up to what? Up to n. So what we are saying, if this one is P of 1, if this one is P of k, this one will be equal to P of what? P of k plus 1, the next integer, the next number. So if P of 2 is true, we are saying also P of 3 must be what? Must be true. So we are going to use P of k to prove that P of k plus 1 is what? Is true. So what do we do here? we need to put P of K plus 1. What is P of K plus 1? We need to substitute this n with K plus 1, also this n and this n with K plus 1. So we've got 1 plus 2 plus 3 plus, here we need to put this K, and then we need the next term, which is the K plus 1 term, which must be also equal to, we substitute an n with K plus 1 and this n with a K plus 1 here, plus 1 over 2, which will give us, here is K plus 1, which is a K plus 2. So this one will give us this result here. And then we all see that this part here, this whole part is also equal to this whole part here in our assumption step, in our hypothesis step, which means we can also substitute this whole part here with this part. We can just put this part here. So when we add K plus 1 to both sides of the equation in P of K, we obtain this, right? Which means for this one, K plus, we can take this one and put it here so that we can get K plus K times K plus 1 over 2 plus K plus 1. That's what we have. Sorry, that's what we have here. This is this expression. So from there, you can multiply by 2 here or over 2. This is the addition of fractions, which is 2k plus 2 over 2. So if we expand this and factorize, we get up to here where we have the k plus 1 times k plus 2 all over 2. So this last equation shows that P of k plus 1 is true under the assumption that P of k is true. So this completes the inductive step. Why? Because at this step we've got a k plus 1 and a k plus 2 here. So we have actually taken the left hand side and we prove that it is equal to the right hand side, this expression that we have here. So once you manage to prove that the left hand side is equal to the right hand side, you can now give a conclusion. This step is also very important. You need to give a what? A conclusion about what we have been proving. So this last equation shows that P of k plus 1 is true under the assumption that P of k is what? Is true. So this completes the inductive step. So we have proven that 1 plus 2 up to n is always equal to n times n plus 1 all over 2 for all positive integers n. I don't know if there is any question on proving this type of question, this type of problem. Don't know if there is any hint. Okay, I think I can move to the next step. We've got this example, example 2, where we have to use the mathematical induction to show that 1 plus 2 plus 2 squared plus up to 2 to the power n is always equal to 2 to the power n plus 1 minus 1 for all non-negative integers of n. You need to take care of these keywords, non-negative integers of n, which means our n will be from 0, 1, 2, 3 going upwards, because we are talking of non-negative integers of n. So using mathematical induction, we've got 2 steps. the basis step where you have to prove that it also holds for the first position, or for the first integer, and then you give an assumption for P of k, and then use that assumption on inductive step to prove that P of k plus, if P of k is true, then P of k plus 1 is also what is also true. So let's start by the basic step. We have to put P of 0 here. So P of 0 is true because 2 to the power n here, which is 2 to the power 0, any number raised to the power 0 is what? Is 1, right? So 2 to the power 0 is equal to 1. And on the right hand side, we've got 2 to the power 0 plus 1, which is what? 2 to the power 1 here, which will be equal to the power 1 minus 1, which will give you a 1. Therefore, this completes what? The basis step. So if the left hand side is equal to the right hand side, then for the basis step, it's enough. Then on the inductive step, for the inductive hypothesis, we assume that P of k is true for any arbitrary non-negative integer k. That is, we assume that 1 plus 2 plus 2 squared plus 2 to the power k is equals to 2 to the power what? We replace our n here by what? By k is equals to the power k plus 1. We replace also our n here by what? By k, to give us to the power k plus 1, then minus 1. So what will be next? We need to prove that if P of k is true, also P of n must be true for P of what? Of k plus 1 for the inductive step. So to carry out the inductive step using this assumption, we must show that when we assume that P of k is true, then P of k plus 1 is also true. That is, we must show that 1 plus 2 plus 2 squared plus 2 to the power k, which is the hypothesis step, plus 2 to the power k plus 1. We add 2 to the power k plus 1 for the next integer, which is equal to what? Must be also equal to, here on n here, we put a k plus 1, which is equal to the power k plus 1 plus 1, which is equal to the power k plus 2 here. This one will be equal to this one. So what are we going to do here? We need to replace this one with this one. You see that the hypothesis step is equal to this one. So we can take this and replace this one with this expression, which means we end up having something like 2 to the power k plus 1 minus 1 plus 2 to the power k plus 1 is equal to this right hand side, So I'm sure that this is the thing that we have. If we replace this one, we will get this. So here we know that you can take this one and add them. If we take k plus 1 is something like x, let's suppose that to the power k plus 1, and let's suppose that k plus 1 is equal to x. If we say 2 to the power x plus 2 to the power x, we can add these two to become 2 times 2 to the power x, something like this. So that's what we get here, where x is what? Is 2k plus 1. So We need the highlight. So here we know that 2 times 2 to the power k plus 1, since our bases are equal, we can also add powers. So we can add k plus 1 with this one here, so that it will become 2 to the power k plus 2 minus 1. But I think we know this thing here from here. When we assume that p of k plus 1, when we assume our n is equals to k plus 1, we put k plus 1 here and we actually get this expression. So since this left hand side, we consider the left hand side. So since this left hand side is equal to the right hand side, I'm sure that you can now conclude that this statement, or P of n, is true for all non-negative integers of n. So note that we used the inductive hypothesis in the second equation in this string of equalities to replace this one by this. So we have completed the inductive step, because we have completed the basis step and the inductive step. By mathematical induction, we know that P of n is true for all non-negative integers of n. So that is 1 plus 2 plus 2 to the power n is equals to 2 to the power n plus 1 minus 1 for all non-negative integers of n. So please, you need to put a conclusion whenever you are answering this kind of problems. You need to put a conclusion. Do not forget that. I don't know if there is any question before I proceed. There any hand? Okay, I think I can proceed. So there is proving inequalities. There's proving inequalities. So use mathematical induction to prove that for all integers any greater than or equal to 3, which means from 3, 4, 5, 6 going upwards, 2n plus 1 is always less than 2 to the power of n. We need to prove that whenever our n is greater than or equal to 3, then 2 times n plus 1 is always less than 2 to the power n. So we start by the basis step. Here we started by putting our n is equals to what? N is equals to 3, because our n is starting from 3. So for n is equals to 3, what do we get? From the left hand side, we get 2 times 3 plus 1, which is here, which is a what? 6 plus 1, which is equal to 7. So from the right hand side, what do we get? Which is 2 to the power 3, which is equal to 8. So since the left hand side is less than the right hand side, 7 is always less than what? Less than 8. So the statement is true for n is equal to 3. So once we have proved that this statement is true for n is equals to 3, we now move on to the inductive step, where you need to first give an assumption for P of k, and then you prove for P of k plus 1. So we assume that this statement is true for n is equal to what? For n is equal to k. So for the inductive step, suppose that is true. Suppose that P of n is true for n is equal to k. That is 2k plus 1 is always less than 2 to the power k. For k will be greater than or equal to 3. So here, team, what we've actually done is to replace this n by k and replace this n by what? by k. So we need to show that the statement is true for n is equal to what? For n is equal to k plus 1. That is, here we need to put our n as k plus 1 and we put our n as k plus 1, and then we prove that this side will be always less than this side. So if we put our k plus 1 here, it will become 2 times k plus 1, which will be always less than 2 to the power k plus 1. So that's what we have here. So let's consider the left hand side so that we can prove that this side is always less than 2 to the power k plus 1. So we have 2 times k plus 1 as our left hand side. If we expand, we'll get 2k plus 2 plus 1. So if we put this 1 and this 2k together, we end up having something like 2k plus 1 plus 2. But I think we know that 2k plus 1 from P of k. From P of k, where is our P of k? Okay, it's okay. From here, we know that 2k plus 1 is always less than 2 to the power k. So we can take this 2k and replace this one with 2 to the power k. So end up having 2 to the power k plus 2, right? And then from there, we know that our right hand side is 2 to the power k plus 1. 2 to the power k plus 1 is just the same as 2 to the power k plus 2 to the power k. Is another way of writing 2 to the power k plus 1, just like this term. 2 to the power k plus 2 to the power k. It's just the same as what? Is 2 times 2 to the power k. Which means whenever we are multiplying numbers, here we've got the same base here. So we can add powers, which is equals 2 to the power k, k plus 1. So you see that this is another way of writing 2 to the power k plus 1. So here I'm sure that this 2k can also cancel this 2k, or we can subtract both sides. So we end up having something like 2 is less than 2 to the power k. And we know that our k is starting from what? From 3. So so 2 is always less than what? 2 to the power k here. Because if we put a 3 here, or from the basis step, if we put a 3 here, it will become an 8, and 2 is always less than 8. And this one is always an increasing function. So we can conclude that this one, this left-hand side, this side is always less than what? 2 to the power n for P of k plus 1. So you can write a conclusion there. I don't know if there is any question. Is there any hand before I proceed? Are we together here, or I'm speaking to myself?
Yes, we're together, sir.
Okay, thank you. Others, can you confirm?
I have a question, sir.
Okay, you can ask.
Yes, I wanted to ask Kutironi, let's say I failed to include my conclusion. Does it mean you'll deduct marks from the response?
Yes, because the conclusion is also the part of the question. Otherwise, there will be no answer. Because the question will be actually asking you to prove that a certain expression is true, right? So you need to give a conclusion that it is true. So your conclusion is the one that provides the answer to the question. So you need to give the conclusion. And your conclusion will be always simple. Will be always simple. Will be always simple, because what you have to do is to following the steps of the mathematical induction, of the principle of mathematical induction. So like here, we managed to prove that we were being asked to prove that for all integers n is greater than or equal to 3, 2n plus 1 is less than 2n. So we know that since p of k is true in our basic step, and also p of k is true and also p of k is true, not p of k, and also p of k plus 1 is true, then we can conclude that this expression given here is true for n is greater than or equal to 3. So that's like how you formulate your conclusion. I don't know if there are any other questions before we prove divisibility results. Is there any hint? Okay. So let's prove divisibility results. So mathematical induction can be used to prove divisibility results about integers. Example 1. Use mathematical induction to prove that n to the power 3 minus n is divisible by 3 whenever n is a positive integer. Take note of these keywords. So we want to prove that n to the power 3 minus n is always divisible by 3 whenever n is a positive integer, which means you are taking what? N is positive integers, which means you can actually take from 0, 1, 2, 3 going upwards. So I'm sure this is the example. So let's start by the what? By the basis step. Let's take, for example, when n is equal to 1. So p of 1, we will replace n by what? By 1, which will be equal to 1 to the power 3 minus 1, which will be 1 minus 1, which is equal to 0. And you know that which is clearly divisible by what? By 3. Because 0 is always equal to 0 times 3. So you can say that this statement is true for p of what? For p of 1. So therefore the given statement is true for what? For n is equal to 1. So on the inductive step here, suppose that the statement is true for n is equal to k. That is on our statement here, we will put k for n here. Then we end up having k to the power 3 minus k is divisible by what? By 3 for all n is what? A non-negative integer or is a positive integer. Yeah. So then we can write this as k to the power 3 minus k is equal to what? 3k, 3 times q. For some q is a what? It's just a positive integer. It's just an integer. So we need to prove that p of k plus 1 is also true. Once p of k is true, also p of k must be what? Must be true. So this is just an arbitrary integer that we have put here, and we know that any number multiplied by 3 can be also divided by what? By 3. That's the logic here. So if we put k plus 1 for n here, we get k plus 1 to the power 3 minus k plus 1 minus k plus 1 is divisible by what? By 3. So we need to prove that. So if we expand this, k plus 1 multiplying itself 3 times and then subtract k plus 1, we get this minus k plus 1. And then if we further expand this, what do we get here? You get k cubed minus 3k squared plus 2k. And if we factorize, if we put together this k cubed minus k here, and then we are subtracting k and adding a k at the same time, which means we are adding nothing. It's like minus k here plus this k will be equal to 0. So we are subtracting a k and adding a k at the same time, which means we are adding nothing, we are subtracting nothing. So end up having a k cubed minus k. Why do we want this k cubed minus k? Because when you put our p of k here, we have actually assumed that k to the power 3 minus k is always divisible by what? By 3. So we now know that this one is always divisible by what? By 3. If we add these two, we get what? A 3k. So here we can also factorize this one, where we can factor out 3. So we end up having a 3 times k squared plus what? Plus k. And also from here, from this equation that we formulate, we know that k to the power 3 minus k is equal to what? Is equal to 3q. So we can substitute k cubed minus k for 3q. So we will end up having something like this. 3q plus 3 times k squared plus k. So we can again factor out 3, and we have something like this. 3 times k times q plus k squared plus k. And we know that any number multiplied by 3 can be always divisible by what? By 3. So we can conclude that k plus 1 to the power 3 minus k plus 1 is divisible by what? By 3. Hence, by mathematical induction, n cubed minus n is divisible by 3 whenever n is a what? Is a positive integer. That's your conclusion. Without this conclusion, your answer will be not enough for this concept. I don't know if there is any question. Is there any question? Because I'm sure that I've come to the end of my presentation. Are there any questions? So what do you need? Yes, you can ask. Anyone with a question? Okay, so Tim, what do you have to actually do is to practice. because there are a lot of problems that you can solve. So you need to practice. So I think that's all for this presentation. Thank you. So have a good day, team.